welcome to class. Let's go ahead and get started. Okay, so before we get started with today's lecture, I just want to make a quick announcement regarding the assessment. I was really hoping to give you guys the grades back and the feedback by last week, actually, but definitely by this week. I'm still waiting for the grades from your tutors. So they promised me that they will get me the grades today, so hopefully by tomorrow or maximum day after, I will be able to get you guys your grades back and get some feedback to you. So I do apologize for the delay. I was really hoping to get it done by today, but that will be coming very soon. Okay, so with that out of the way, let's go ahead and talk about today's topic. Now, today we're going to really build on what we discussed last week. Last week we talked about the one-way ANOVA, so we're going to do a quick review about your one-way ANOVA, and then we're going to talk about the tests you need to do to follow up on the one-way ANOVA if you get a significant result. And these are your planned contrast and your post-hoc tests. Okay, so what happened last week? Last week, we talked about the one-way ANOVA. It's the analysis that you will conduct if you have 3 or more independent groups. Guys, shh, please let everyone listen. If you've got more than 2 groups, so 3 or more groups, 1 independent variable, and you want to know, is there a significant difference between these groups? Now, as we discussed last week, we will look at the one-way ANOVA by assessing the overall variance in the data and comparing the variance we can explain to the variance we cannot explain. And then we ended it with, okay, there's a significant F, and that's all we can conclude. We can't actually determine whether there is a difference between which groups, right? We said that's for next week, and well, today is now next week. So today is where we're going to pick up from last week, and we're going to talk about how we can determine if you get a statistically significant F ratio. Great, we can explain an overall amount of variance in the data that is reliable, fantastic, but that doesn't tell us which group differs from which group. So that's what we're going to be focusing on today. All right, so last week we went through 2 different methods for conducting an ANOVA using SPSS. Now again, remember that when we conduct an ANOVA, it's looking at that variance we can explain, looking at that systematic variance, right? The variance that is systematic to group assignment. And we're comparing this to the variance that is unexplained, or the variance that is unsystematic. And if you go through the compare means menu, you can get an ANOVA here with the sums of squares, the degrees of freedom, mean squares. And this gives you your F ratio. Or you can go through the general linear model menu, get the exact same thing. So 2 different ways of getting to the same answer. Both of these are going to produce an ANOVA table with the same information. It tells you your sums of squares. Remember that the sums of squares is the sum of the squared error. It is the difference between what we expect with our model, in this case being the group means, and what we would expect using that overall basic model, which is just the mean of y, right? It's just the squared variance. The sums of squares error, or the within variance, is the error that we get between what we predict using our model and what we actually observe, right? We would predict that everybody in the group beginning should be scoring at a 12.4, whatever it might be. But of course, there's variance within groups, so why do we get this variance within groups? That's your sums of squares within, or the sums of squares error. This is the variance we cannot explain, right? It's due to the other stuff that's influencing behavior. Then we have our mean squared, which is just the average amount of error. So it's just taking that sums of squares and dividing it by degrees of freedom. So it's literally just taking like an average. Same way that if I was to take all of you guys' height, and then I take the sum of the heights divided by the number of participants, that gives me an average. Same idea here. So it's just the average amount of variance we can explain, and we're going to compare that to the average amount of variance we cannot explain, and this is that F ratio. Okay? So this is what we talked about last week. And again, the F ratio is a ratio of variance explained, that mean squares regression, or the mean squares model, the mean squares explained, however you want to describe it, all refers to the same thing. is the variance we can explain is the treatment effect relative to the error in our model. So we're comparing the variance we can explain using the group means relative to the overall y. We're doing this using the F ratio. The F ratio, again, many ways to describe this, right? It can be thought of as the mean squares model to mean squares residual. You can think of this as the explained variance relative to the unexplained variance. You can think of this as differences between groups relative to differences within groups. Treatment effect versus like error. There's so many ways to describe this. It all kind of comes down to the same idea. This is also the same idea that we discussed when we did linear regression, right? It's the same thing. It's same basic concept of looking at the variance we can explain using our model versus the variance we cannot explain because it's just due to other stuff we're not including in our model. Okay, so we went through this whole rigmarole. We got a significant F ratio. We recall last week we were looking at the effect of swearing, of including a curse word when we're trying to persuade somebody. And we wanted to know, does including a curse word increase the persuasiveness? And if so, does it matter if the curse word comes at the beginning or the end of the message, right? So we have the three conditions. We conducted an ANOVA. We got a significant F ratio last week. Great. Significant amount of variance that we can explain, or a reliable amount of variance that we can explain. Doesn't tell us which group differs from which group. So this is why we need to conduct additional tests to now identify where is the source of the variance, which group actually differs from which other group reliably. Now, I also mentioned last week that the reason we conducted an ANOVA is because if we do just repeated t-tests using the same groups, this is going to inflate your family-wise error. So we can't just do a bunch of t-tests. We have to do the ANOVA to hold constant that family-wise error. Okay. We still want to know, though, which group differs from which group. Does the beginning differ from control? Does end differ from control? Does beginning differ from end, right? We still want to know these things. So if we can't do this, how should we do it? All right, so go into WooClap and see if you can think about some ways in which you might compare multiple groups, but without inflating your family-wise error rate. Okay, some people definitely did the reading. I'm seeing some good terminology coming up, so that's great. Good job. Okay, so I'm seeing a lot of really good responses here. And yeah, like I said, it's clear that some of you guys definitely did the reading, so excellent. Now, a couple of key answers that are coming up here is adjusting the p-value, right? Or reducing the p-value. And that's really what we're going to come down to a lot of this, is we're going to be adjusting the p-value. Remember that the problem with the family-wise error is that we want to maintain that 0.05 alpha criterion. But when we do multiple comparisons using the same groups, it's no longer held at 0.05. It gets inflated. So what can we do? Well, yeah, one obvious thing we can do is just reduce the p-value for each one of the contrasts so that when we combine them, we're still overall keeping that 0.05 alpha criterion. And that is the underlying goal for many of these tests that you guys have mentioned up here. Now, I see some things looking at planned contrast, post hoc. We're going to talk about those. And those are general terms. Those are umbrella terms for lots of types of comparisons that we will make. all with the goal of allowing us to do multiple comparisons, but without inflating that family-wise error rate. Okay, good answers, guys. Okay, so let's move on and talk about these ways in which you might do these multiple comparisons. We're going to start off with planned contrasts. So planned contrasts and post hocs. These are two, like I said, umbrella terms for different types of, or different approaches to doing these multiple comparisons. Now, planned contrasts, as the name suggests, means you have planned these in advance, right? And guys, most of the time you should know the analyses you're going to conduct in advance, right? It's based on the hypothesis you're making. So based on what you have hypothesized, you should already know what you want to compare. Which groups do you want to compare in order to test your specific hypothesis? So you've planned these comparisons or these contrasts in advance, right? They're called planned contrasts. Now, the key with a planned contrast is that you are comparing two sources of variance. Okay, it's always just two sources. Now, those sources of variance can be chunks of sources. Now, we can combine sources of variance, or we can divide a particular source of variance into smaller subchunks, but we're always going to be comparing A versus B. All right, so let's go through this. Now, the book talks about two types of planned contrasts, orthogonal versus non-orthogonal. It doesn't make a huge difference. The only thing to know is that orthogonal means that you're never reusing the same groups. Non-orthogonal means, yeah, you're reusing the same groups. That's really the only difference. I don't think it makes a huge difference beyond that. So let's go through a couple of the orthogonal contrasts. Orthogonal meaning we're not reusing the same groups, but we will be chunking it differently. Let's say we did our analysis, our ANOVA. We got a significant F, and I want to know, okay, what hypothesis do I need to test? What do I first need to think about? Well, I want to know, will having a swear word in my argument increase the persuasiveness of the argument relative to not having a swear word? So I'm comparing, in this case, my control group with my two experimental groups. I want to know, what is the effect of having a swear word? I don't care at this point if the swear word comes at the beginning or the end. I just want to know treatment versus control. Almost like a t-test, right? So this is my first comparison that I want to run. So I'm going to chunk my two experimental groups together. I'm going to combine them together so I can use their combined effect to compare to my control group. Does that make sense? So I'm going to compare group control to the combination of beginning and end. Now, to represent this, I'm going to assign a weight to each one of my chunks. So beginning and end each get a weight of 1. Now, we always just do full numbers. There are some statistical software packages where you can do partials, like a 0.3, 0.5, whatever. For SPSS, it's just whole numbers, 1 or -1, or 2, 3, whatever it might be. So I'm going to give each of these a positive number of 1. And to balance this out, to give the control group a balanced versus the other two groups, I'm going to give this a -2. Now, the key is that the sum of your weights needs to add up to 0. As long as the sum is added up to 0, you're doing fine. So I'm going to compare beginning and end. I'm going to put those things together. So I'm going to give them the same weight, 1 and 1. And I'm going to compare it to my control group. And I'm going to give this a weight of -2 to balance out the positive 2 that comes from my experimental groups. Now, does it matter that I gave the control group a negative value, and the experimental groups a positive value? Not at all. I could have given this a -1, and positive 2. Doesn't matter. As long as they add up to 0, it doesn't really matter. Now, it does matter in the sense I shouldn't be giving end a -1, control a -1, and beginning a plus 2, because that's chunking them differently. So obviously the things you want to chunk together, the things you want to put together should have the same weights together. All right, any questions so far? So this contrast allows me to compare group control with the 2 experimental groups that have been combined, that have been chunked together. I can now assess, is there any effect of presenting a swear word on persuasiveness of the message? But that's not all I want to know. I do want to know, what is the effect of the placement of the swear word? Does it matter if the swear word occurs at the beginning or at the end? That's also important, right? So now I want to compare these 2 groups. I don't need to include the control group. I just want to compare group beginning versus group end. So I need to assign weights. One of them is going to get a positive 1. One of these will get a negative 1. Again, it doesn't matter which one I give positive and negative, as long as they have opposite values and they sum to 0, that's all that matters here. So control gets a weight of 0, which tells the SPSS program, don't include it in this comparison. So anything you don't want to include in your contrast, just give it a weight of 0. Okay, any questions so far? Okay, now this is an example of a orthogonal contrast where I'm not reusing the same exact chunks. You saw that in the previous one, we're comparing group control versus the combination of beginning and end. So that's one chunk. And in the second contrast, I'm separating group beginning and end. So that's a different chunking combination. So we're not reusing the same exact chunk across multiple contrasts. A non-orthogonal contrast will just reuse the same chunks. And it's going to control for the family-wise error by adjusting the p-value. It doesn't honestly matter a huge amount. Like the distinction of using an orthogonal versus non-orthogonal doesn't really matter. These are just 2 ways of thinking about your contrast. But if you want to compare the same things over and over again, also fine. Just make sure you're adjusting for the p-value. And if you do this through SPSS or whatever stats package, it will do it for you if you're doing it through the planned contrasts. So a non-orthogonal might be, okay, do each of my experimental groups differ from my control group? So I'm going to compare end versus control. Here, beginning gets a weight of 0. I don't want to include it in my contrast. Control will get a -1, end gets a positive 1. So the sum of these 2 weights is 0. And the second contrast, we'll look at beginning versus group control. So now beginning gets a weight of +1, end gets the weight of 0, control continues to be weighted at -1. So you can see I'm reusing this same chunk of control across multiple comparisons, which is why this is called a non-orthogonal contrast. As long as you have the chunking the way that you want to test your specific hypotheses, don't care about whether it's called orthogonal or non-orthogonal. So you can determine the kinds of chunking or the kinds of contrast you want by loading these into SPSS and doing these kinds of custom tests. There are some pre-loaded contrasts in most stats packages, including SPSS. These are specific kinds of contrasts that are just commonly used ones. So if you know you want to use one of these kinds of contrasts, you don't have to go through the effort of inserting the weights yourself. You just say, hey, please run a Helmert test, or run a simple contrast, or run a repeated contrast, because then it just makes it a little bit easier for you. You don't have to enter each contrast into your stats package. So it's just a shortcut. So these contrasts, you have a few different options. Deviation, you have options first or last. And what this means is that you're going to compare the effect of the all the groups together, 1, 2, 3, 4. So let's just pretend we've got 4 groups here. Against, in this case, the second group, compare all of the groups together against the third group, and all of the groups together against the fourth group. This is using your first group as what we call like a reference group. But you can also do a deviation with last as your reference, which just means you compare all of the groups against the first, all of the groups against the second, all of the groups against the third, but not against the fourth. So depending on what you want to use as your reference, right? So whichever one is coded as 0, that will be your reference. So if I have, for example, put it into SPSS, group control is labeled 0, group beginning is 1, and group end is 2. That's how I've labeled my categories. Then I might use first as my deviation first. If I said group beginning is labeled as 1, group end is 2, and group control is 3, then I might use last because my deviation, or my last group, my third group, is my control group. So just think about, is your control group the first or the last in your, when you have coded them into your SPSS? Simple just means that you are comparing each group against either the first or against the last. And again, you get the option to choose first or last as your reference group. And choose it based on how you have coded your variable. Is your control group labeled as the first in your group as 0 or 1, or is it labeled as the last in your SPSS? Repeated just means you're going to do a contrast against the next one. So 1 versus 2, 2 versus 3, 3 versus 4, so on and so on. Okay? Helmert means you compare the first against the combination of everything that comes after it. Then you compare the second against everything that comes after it. Then the third against everything that comes after it. So each level gets compared to the combined groups that are later. Versus different, where it's just the opposite way around. The last group gets compared with everything that comes before it. Third group gets compared to everything that comes before it. Second group gets compared to everything that comes before it. So it's just the same thing but opposite. Again, these are just different types of contrasts. You may or may not use them. Depends on the kinds of contrasts you want to run. If you know that you want to run a simple contrast, which is quite common, right? We want to compare each group relative to our control group. Maybe instead of having to put each contrast into SPSS one at a time, and that takes a bit of time, just tell SPSS to run a simple contrast, and it's going to do it for you. So it's just a way of shortcutting it. And then finally, we can assess for polynomial trends using SPSS. This will look at the overall trend in the data. So if you have, let's say, a linear trend versus a quadratic, a cubic, or a quartic, these are just different ways in which the data might be shaped. Gives you a bit more information about the data. Okay, quick summary here. Conducting several t-tests on the same groups will increase the risk of inflating family-wise error. So the planned contrasts allow you to make multiple comparisons while maintaining the type 1 error rate. And it does this by doing systematic chunking of groups together, so you're not repeating the same groups, or it will adjust the p-value to keep the alpha criterion at 0.05. So you're going to partial out sources of variance and decide what you want to compare. So think, I want to compare group control versus my 2 experimental groups, or I want to compare my 2 experimental groups together and not with control. So you have to think about what you want to compare. And then the planned contrast can be made between individual groups or combinations of groups. That's really the strength of the planned contrast, is that you can combine groups together to compare against another group or another combination of groups. So it really allows you to chunk these things together. I want to compare my 2 control groups against my 2 experimental groups, right? That may be very helpful. So it just allows you to chunk these different sources of variances together to compare against each other. So weight each chunk that you want to compare so that the sum is equal to 0 across all of your groups. And then polynomial contrast, check for trends and the data across groups. Any questions before we continue? Okay, so let's do this in SPSS. So we have conducted our ANOVA. We know that there's a significant F ratio. We want to see where the difference lies, which groups are different from which groups. So we have to think, again, what am I going to compare? I want to compare my 2 experimental groups versus my control group. So this is the first contrast I need to think about. My 2 experimental groups are going to get both a positive 1. My control group gets a minus 2. Again, it could have been the other way around. Doesn't matter as long as the sum is equal to 0. I also want to compare my 2 experimental groups, beginning and end. So one of these is going to get a positive 1. One of these is going to get a negative 1. My control group will get a weight of 0 because it's not going to get included within this within this contrast. So these are the 2 contrasts that I want to run. So I'm going to click up here where it says contrasts. First thing, let's just check for this polynomial trend. So because we've got 3 groups, we can check for a quadratic trend. We can have different options here, but let's just check for quadratic since we have the 3 groups. It will automatically check for the quadratic plus anything less than that. So it will automatically also assess for linear trends as well. If you choose a cubic, let's say we have 4 groups and you do cubic, it will also automatically assess for quadratic and linear. So just choose the highest level you can. Okay, now when I talked about like how did you label your groups in SPSS, remember when you entered your variables, you chose to label them with a particular value. So in this case, control is equal to 0, beginning is labeled as 1, and end is labeled as 2. So control is my first group. It doesn't really matter the way that you enter them in. I could have put control as my last group. Now you should put your control either as your first or your last. It doesn't make sense to put it somewhere in the middle. You shouldn't do beginning, control, end. That doesn't really make sense when you want to do your contrasts. So either make your control group the first variable or your last one, because you guys already saw that when we do those those preloaded planned contrasts, you get the option first or last. And so this just makes it easier to run those kinds of things. So I have put my control group as my first one, as 0. And there's a specific order here. It goes control, beginning, and end. So when I put my weights into SPSS, it's going to correspond to the way in which I entered or I labeled my variable here. So I'm going to enter minus 2, 1, and 1. And this corresponds to exactly the groups and how they're ordered. So minus 2 is for group control, positive 1 is for beginning, positive 1 is for end. So the order in which you enter the weights should correspond to the order in which the groups are labeled in SPSS. If control had been my last group, so it's like beginning and control, then it should be 1, 1, minus 2. Okay, any questions? Now do note that SPSS is really helpful and tells you, hey, yeah, the sum of these weights is equal to 0, which is good, right? That's what we want. If the sum of the weights is something else, then you need to go back and do the weights here because you've made a mistake. Remember that the weights need to add up to 0. So just go back and double check that, but it makes it easy for you right here. Now, we want to run 2 contrasts. So we're just going to click the button that says Next. And we're going to add our second contrast. And we should see that this is contrast 2 out of 2. So maybe we want to run 3 contrasts, 4 contrasts, however many contrasts you want to run, that's fine. Just click the button Next and add in the weights there. So now I have 0, 1, minus 1, which corresponds to group control having a weight of 0, group beginning have a weight of positive 1, and group end having a weight of minus 1. Okay, does this make sense now? Okay, so when you do the contrast, that's all you need to do. Click OK, and then you get your ANOVA again. So you're going to get, at first, the ANOVA that allows you to assess for the, well, the first thing is the ANOVA table, and you should note that the between groups, within groups total, this is exactly the same as what you guys saw before. So this is just replicating the same ANOVA table, same exact results. But it also includes information that allows us to check for the polynomial trends. Now, it gives you both weighted and unweighted. Weighted is accounting for different group sizes. So the first thing we can look at is that the linear term, so are we checking for a linear trend? If it is unweighted, that is pretty close to being significant, but the weighted is significant. So this suggests that we do have a significant or a reliable linear trend in the data. But there doesn't appear to be any kind of quadratic trend. So this tells us that the data fits a linear trend, not quadratic, which kind of fits with what we see in the graph as well. It's clearly not quadratic. It's sort of linear, but it's definitely not quadratic. All right, more, I think, interesting is we look at the planned contrasts here. First thing, the planned coefficient, or the contrast coefficients tells us what are the contrasts. In case you forgot, or in case they show up on a test that you haven't actually put them into yourself, right? This tells you what are the contrasts that are being conducted here. Contrast 1 tells us we're comparing group control with beginning and end. Contrast 2, we're comparing group beginning with group end. So we always know that contrast 1 is comparing treatment versus control. Contrast 2 is comparing our two treatment groups. So now we go down. We've got two contrasts here, contrast 1 and contrast 2. But we've got two options. Assume equal variances, does not assume equal variances. So now we need to think back to what we did, what we learned last week. Last week when we did an ANOVA, we did check the Levene statistic to check the assumption of homogeneity of variances. Recall that this is one of the assumptions for doing an ANOVA, that the variances between groups is roughly the same. We don't want to have one group that has a lot of unsystematic variance and one group with very little unsystematic variance, right? We want there to be roughly similar unsystematic variance across my three groups. And so we're looking for a non-significant Levene's test. That is what we found last week. So therefore, we can assume equal variances. We can use this top part here. And when we look at our contrasts, what we see is a t-test, because we're doing basically a t-test, right? We're comparing two things. So we're just going to compare chunk 1 with chunk 2 over the standard error. And the t-test for contrast 1 is significant, right? T is equal to 2.72, or 2.7. P-value is less than 0.05. This tells us that there is a reliable difference between having a swear word and not having a swear word on the persuasiveness of the message. Okay? Contrast 2, right below it. T is equal to 0.63. P is greater than 0.05. This tells us that there is not a reliable difference between our two experimental groups. The persuasiveness of the message does not change when you put the swear word at the beginning or at the end. So when we get that overall significant F ratio, yes, there is a reliable amount of variance we can explain. Now we know why that F ratio is significant. It's because when you compare control versus your other two groups, that is reliable. That gives us a reliable amount of variance that we can explain. And it's not necessarily that our two experimental groups differ from each other, but rather the combined groups of our treatment groups differ from our control group. Okay, any questions so far? All right, and then we have our effect size here. So we can look at the effect size for each one of these to determine like how big of an effect do we have. Okay, so this gives you more information about your ANOVA. We got a significant F ratio. Great. There is a reliable difference between the groups. Now we know exactly which groups differ from which groups, or at least we know somewhat, right? We know that our two experimental groups can differ from our control group, but combined. But what about those preloaded, ready-made contrasts that we talked about, right? So instead of having to enter each contrast manually, maybe I could just use a preloaded one and save myself just a little bit of work, a little bit of time. You can't use these from the first menu. You have to go to the second menu option. So we have to go through the general linear model menu option. So go to univariate, put in your variables just like you did normally for an ANOVA, and then go to contrasts. If you go down to contrast, you can now choose which contrast you want to run. So I'm going to choose difference just because I chose one at random. Remember that difference means that we're going to compare our last group to the combined higher groups. Our third group gets combined to everything that comes before it as well. Second group gets combined with gets compared to everything that comes before it. Now, because my control group is the first, it probably would have made actually more sense to use a Helmert test instead of a difference test, but this is just an example. All right, so I'm choosing a difference contrast. The first contrast says level 2 versus level 1. So it's going to compare level 2 versus level 1. And we can see that this contrast is significant. So when we compare group beginning versus group control, this is a significant difference. Second contrast, group 3 versus everything that comes before it. So now we're going to compare group end versus group beginning and control combined. This is not significant. This contrast has a p-value of more than 0.05. Again, for this particular example, a Helmert test probably would have made a bit more sense, but you guys understand the concept. When we're doing a preloaded contrast, it will tell you, it will just do it for you. So I could have run a Helmert, and that would have been first versus everything that comes after it, second versus everything that comes after it. And again, this is just a way of identifying if you get a significant F, which groups differ from which groups. Because the F ratio alone doesn't tell us that. We have to conduct additional planned contrast to identify exactly where that difference lies. And we have multiple options of doing so. You can either use your own custom contrast where you enter the weights, or if one of these preloaded contrasts already matches what you wanted to do anyways, just do that and save yourself a little bit of time. Now, at the bottom of this table, it's also going to give you another ANOVA table. This is matching exactly what the ANOVA shows you from before, so you can kind of ignore that because you've already seen the ANOVA table. All right, so that's it. So check the coding of your categorical variables. Is your control group coded first or is it coded last? Enter the weights according to the way you have coded your variable. Use the preloaded contrast to save yourself some time if they match the contrast or the hypotheses you want to test. Any questions? Yes. Yeah. So why did I say that? Why should we use Helmert? Helmert is the opposite. So let me go back to Helmert. Hang on. So if you recall, the Helmert test compares the first to everything that comes after it, the second to everything that comes after it, the third to everything that comes after it. The difference test compares the last to everything that comes before it, the third to everything that comes before it, the second to everything that comes before it. So they're the same thing, but just opposite. Now, when I coded my variable, my control group is coded first. So it makes a lot more sense to use this one where 0 compared to groups 2 and 3, and then 1 compared to group 2. The difference test will compare groups end with groups beginning control and group beginning versus control. So just because of the hypothesis I want to test, it just makes a little bit less sense here, right? It's just because of how I coded my variable. Does that make sense? Good. Yeah, other questions? Yes. Yes. So in the example I gave you guys, when we did these things manually, we compared in contrast 1, control versus both of your experimental groups combined together. Contrast 2, experimental 1 versus experimental 2. So the question is, which preloaded contrast might be most appropriate? So then we have to think about, again, where's my mouse? There. Look at the way that you've coded your variables. So control is coded as the first, and then beginning and end are coded as second and third. So if I want to compare 1 versus 2 and 3, Helmert probably makes the most sense because Helmert is going to compare 1 versus everything that comes after it. And then it will compare number 2 versus everything that comes after it. So if I want to replicate exactly the same contrast that I did manually, I should do a Helmert test here, right? Because that's going to compare 1 versus all the lower levels. So it's going to compare control versus beginning and end combined. And then it's going to compare level 2 with everything that comes below it. And in this case, it's just one more level. So that will replicate exactly what I did manually. Good. Other questions? Yeah, it just means that I'm not really testing my hypothesis here. I'm just giving you guys an example, and I didn't want to give you the exact same contrast because I want to show you just differences in how the information comes out.
So the right thing to do would have been
the right thing to do would have been just using Helmert because that would have replicated exactly the manual one. I wanted to give you guys, show you other ways of doing it, basically. Yeah. Good. Other questions? Now again, note that if I had coded this the other way around, if control had been my last group, then this would have been the right one. Okay. Okay, so that's your planned contrasts. Planned contrasts allow you to chunk groups together to compare against another group or another chunk of groups. You need to know what hypotheses you want to test in advance, hence planned, right, beforehand. But we can also run post hoc comparisons. Post hoc means like after the fact. So post hoc comparisons, you guys remember that I told you, we don't run multiple t-tests without controlling for the family-wise error rate. However, if you control for the family-wise error rate, then we can run multiple t-tests, basically. That's basically what the non-orthogonal planned contrasts are doing anyways, is they're just adjusting the p-values. Post hoc comparisons are going to adjust the p-value, they're going to adjust the alpha criterion to maintain a 0.05 alpha criterion. So even though you're reusing the same groups across multiple contrasts, you're not going to inflate the family-wise error rate above 0.05. Now, there are lots of different options for post-hoc comparisons. They're all just different ways of comparing groups and adjusting the p-value. Honestly, I always have to go back and re-look what each of these means. The only one I can always remember is that LSD is no correction whatsoever. Bonferroni is the strictest one. Bonferroni will take the number of comparisons you're doing and dividing by the take 0.05 and divide by the number of comparisons you're doing. So it's going to be the strictest. Beyond that, they're all really good to look at. Look at your book to determine what the differences are, because there's a lot. These are all just different ways of adjusting the p-value. Some of them are used when you have equal group sizes. Some of them are used when you have unequal group sizes. Some of them are used when you have homogeneity variances. Some of them you should use when you do not have homogeneity variances. They are just different ways of adjusting the p-value. Look at your textbook to look for the specifics. Just know that LSD, no adjustment whatsoever. Not a good one to use because you're not adjusting the p-value whatsoever. It's literally like rerunning multiple t-tests. Bonferroni, strictest, most conservative. If you want to be absolutely sure, that's usually the one we go for. All right, so I'm going to run several post-hocs so that way you guys can see the differences and how conservative each of these are. So I'm just going to pull out a few random ones here. So we go to post-hoc and just click whatever ones. And obviously you can choose multiple post-hocs. And sometimes I do. When I run these, I will choose a few post-hoc comparisons in case I, for whatever reason, just curious. Okay, lots of information here. Don't freak out. Each of these is looking at the same comparison, again, just applying a different adjustment. So let's just look at the top line for each one of these. Beginning versus control. Now the post-hoc is always going to compare each group with each other. So it's beginning versus control, beginning versus end versus control. The post-hoc comparisons will always look at each comparison, all possible comparisons. There's no chunking. So we're not going to compare one group versus multiple groups. It's always one versus one, and it's going to do all possible comparisons. So we'll start with just looking at the beginning versus control. And what I want to point out is when we look at the p-value under significance, you can see that for some of these contrasts, the p-value meets that 0.05 threshold. It is below 0.05. For some of them, it is above 0.05. So my point being that different contrasts have different levels of conservativeness. LSD, least square difference, like I said, does not adjust the p-value. It is literally like you're running multiple independent t-tests. That's not the one you should ever use. And you can see, if we look at LSD, right there in the center, the p-value is 0.018. So that is definitely the least conservative of these contrasts. Bonferroni takes that 0.05 alpha criterion and divides by the number of contrasts. So we've got 3 contrasts, beginning versus end, beginning versus control, end versus control. So it's going to take 0.05 and divide by 3, and that's the new p-value that you have to meet to be significant. Bonferroni has a p-value just above 0.05. So this is more conservative. It does not meet that threshold for being statistically significant. Same contrast. For LSD, it's significant. For Bonferroni, it's not significant. So the exact same contrast, beginning versus control. For some of these post-hocs, will be a significant difference. For some of these, not significant. Why? Because each one of these tests adjust the p-value in a different way. So that's why you need to think about what kind of adjustment you want to apply to your data and be able to justify, I am using the games how because I am using the Shefe because. I am using the Tukey's test because. So you can choose different post hoc tests, but make sure that you can justify why you're choosing this one. Because as you can see, some of them are less conservative, which means it's easier to meet that 0.05 criterion, which means you are perhaps a little bit more likely to be making a type 1 error. Yes? Sorry, say that again? Yeah. Yes. No. So yeah, good question. That's already been adjusted. So you just now need to look for anything that's below 0.05. It's already done the adjustment for you. Yeah, good question. So all of these have different adjustments that they've made to the p-value. Now you just need to look for the 0.05. So you don't need to do any adjustment on your own now. That's the beauty of it, is it's done it for you. So Bonferroni, it's 0.053, which means it is saying it's not significant difference. You don't need to apply any further adjustments to it. The Games How, also not significant, but you can see that the Tukey's HSD and the LSD, those are both significant. Okay, any questions so far? Now, I didn't do it, but you can go through each of these lines, right, and compare for each of the contrasts which tests say that they're significant, which tests say they're not significant. Now, you shouldn't just shop around, right? I'm showing you multiple post hocs because I want you to be able to compare and see the differences and how conservative each of these tests are. Normally, you have a reason for choosing specific post hoc tests. Normally, I might choose one that assumes unequal variance. So I might choose one that is specifically for violations of homogeneity variance. Because I'm choosing these post hocs as I'm running my ANOVA, so I don't know yet if I have met this assumption. So I'll just go ahead and throw one in that controls for violations of homogeneity variance. Usually I will put in the Bonferroni test because that can apply to pretty much any data set in terms of unequal sample sizes, right? That's always good. If I have equal sample sizes, which is rare, then I might choose a different test that allows for, that corrects based on equal sample sizes. But because I rarely have equal sample sizes across my groups, I usually just will use a Bonferroni. Don't just pick a whole bunch and then choose the one that gives you the significant result, right? Because then you're just kind of cherry picking your data. So do have in mind when you're choosing the post hocs, which post hocs are most appropriate given the data that you have. Are you likely to violate homogeneity variance? Then choose one that will correct for this. Do you have unequal sample sizes across your groups? Make sure to choose a post hoc that accounts for that. If you have equal sample sizes, then fine, choose one that maybe allows for that as well. Don't use LSD. LSD does not correct for the alpha criterion, so you're going to, it's just, no one's going to believe you if you use that one. Okay, so these are a few post hocs. Now, there's a couple of post hocs that deliver the results in a slightly different way. So Tukey's HSD and the Shefe. These are showing you the groups that are chunked together that don't differ from each other. So subset 1 for the Tukey's puts control and end together, and it says these are not significantly different from each other. So group control and group end don't differ from each other. Group beginning and group end do not differ from each other. So it's kind of comparing them, but in a slightly different way. It's telling you these groups belong together. They don't differ from each other. These groups don't differ from each other. Now, from this, you can kind of infer that beginning is different from group control. That's not exactly what it's showing you here, but it's just showing you, hey, group beginning and group end are not differing from each other. Group end and group control don't differ from each other. Okay? Now, Shefe just says, hey, based on the way that I've adjusted the p-value, actually all three groups belong to the same subset. They don't differ from each other at all. Again, just different ways in which it has adjusted the p-value, so it comes up with a slightly different contrast. So the Tukey's, you can infer that group beginning differs from group control, because group beginning is never put into the same subset as group control, right? In the Tukey's test, control is grouped together with end, and beginning is grouped together with end, but beginning is never grouped with control, so you can infer that there's a significant difference between group beginning and group control. But your Shefe test says there's not a significant difference between any of your three groups. They all belong to the same subset. P is greater than 0.05. Again, these are just more post hocs, different ways in which it's displaying how the difference is here. All right, any questions? Okay, so when do you use them? When should I use which kind of contrast? Plain contrast should be used to compare combined groups. This is really the strength of the plain contrast, is that I can chunk groups together to compare against another group or another chunk of groups. So it's used for testing some hypotheses that you have planned in advance. Post hocs are used to compare one group against the other. So it's always comparing all possible groups. So 1 versus 2, 1 versus 3, 1 versus 4. 2 versus 3, 2 versus 4, 3 versus 4, right? It's all those possible comparisons you can make. But it's always one group against one group. And it's just going to reuse the same groups across those comparisons. You can use post hocs also for truly unplanned comparisons. Like if I'm doing a study and it's exploratory, I don't really know which groups are going to differ from which groups, so I don't have in mind some kind of planned contrast. I might just run post hocs because I'm just going to see which groups differ from which groups. Of course, if you do this, acknowledge that this is truly post hoc. Now, you don't have to be truly post hoc. This is like, I will oftentimes run my post hocs because I don't necessarily need to chunk them together. I just want to see, is one different from 2? Is 1 different from 3? Is 2? Because that's actually what I'm testing. So I will just do a post hoc comparison since it does that for me, and I don't have to bother with the whole planned comparisons weighting nonsense. Do whatever makes sense. And sometimes you might want to do both. You could be doing both, where you do planned contrast and post hocs. It just depends on what you are testing. So it all depends on the hypotheses you have stated when you designed this study. Planned contrast, really good for comparing chunks of groups, so chunks of variance. Post hocs, 1 versus 1, always. Okay, so post hoc comparisons test one group versus another, and these can be pre-planned or truly post hoc. Different procedures use different adjustments to the p-values to control for family-wise error rates, which means that some are more conservative than others. Any questions? Okay, so big picture. You've done your ANOVA. You found a significant F. Excellent. Now, what does this F ratio mean? Well, it means that there is a reliable difference between the groups. You still need to conduct these analyses to determine which groups differ from which groups. So then think, okay, do I want to run planned contrast? Do I want to run post hocs? And that just depends on the hypotheses you are testing. That's it. It's just ways of identifying which groups differ from which groups. So to write up your results, just an example. You don't have to follow this exactly, but this is an example, right? You already write up the ANOVA, and then you could talk about what kinds of contrasts you ran. So maybe you conducted 2 planned contrasts here. Where's my thing? So 2 planned contrasts, and then indicate what the contrasts were and whether there was a significant difference or not a significant difference. Or you could say, hey, I did post hoc comparisons. I used this kind of correction. I used the Bonferroni correction, or I used a Tukey's HSD correction, or whatever kind of correction you used, right? And indicate which groups differ from which groups. And then just include your conclusion. So this is the kind of thing you might write after you write up the main results of your ANOVA. Okay, so that's it. Nice short lecture again today. So ANOVA indicates if the systematic variance between groups is greater than you would expect by chance alone, given the unsystematic variance that exists within your groups. The ANOVA, however, does not tell you which group differs from which group. So this is why we need to run planned contrast and or post hoc comparisons. So the planned contrast allows you to combine groups with other groups to compare them together, whereas post hoc comparisons only compare one group with another group. All of these are ways of controlling for that family-wise error rate so that when you do multiple comparisons, you're not going to inflate your type 1 error rate. That's it. So if you have any questions, go back to your textbook, chapter 12, where it talks about these things. You can always write questions on the discussion forum. You can always make an appointment with me during my office hours, or if those don't work, just email me. I'm happy to meet you at other times. Okay, so let's do the quiz yourself. So go ahead and go back to the WooClap. So what should the contrast sum to? Anybody else need this? Okay, yes, overwhelmingly, the correct answer is 0. So your planned contrast, the weights should sum to 0. Okay, good. Next question. Why do you need to conduct planned contrast or post hocs? Okay, yes, correct answer is the first one. The omnibus ANOVA simply indicates that there is a significant difference between your groups. It indicates that there is a reliable amount of variance that we can explain. It doesn't tell you which variance you can explain. It doesn't tell you which group differs from which group. That's why we're conducting these additional tests here. So it's not that it doesn't control for family-wise error. It does overall. The omnibus ANOVA does control for family-wise error as a whole. All right? That's why we're doing it and not doing multiple t-tests. Good. Why should you use planned contrast or post hocs instead of the normal t-tests? I think I just answered this question, but okay, correct answer, yes, because they control for the type 1 error rate that might otherwise be inflated by doing multiple comparisons using the same group. This is why we have to start off with that omnibus ANOVA. So we can't just start off doing a bunch of t-tests. We start off doing the ANOVA. Is there a reliable difference between the groups? If so, great. Now we conduct those planned contrasts, those post hoc tests that then control for family-wise error by adjusting the p-value. Good. All right. Last question here. What is the main difference between planned contrast and post hoc comparisons? Yes, correct answer is D. Plan contrast test specific hypotheses, and they allow you to chunk groups together. Post hoc comparisons can compare all possible combinations of groups, but only one group at a time. Okay, so that is it. Now, for your homework for this week, go back to the same data that you've been using, looking at the concussions and mice and their escape latency. Last week, I asked you guys to conduct a one-way ANOVA, and if you did it, do note that I posted the answer key onto Canvas, so you can find the answer key there. But I want you guys to go back and now rerun your ANOVA, but now use either plan contrast or post hocs to follow up that ANOVA that you got. Okay, last thing, guys. Next week is Diwali, so happy Diwali to those who celebrate. We will not be holding class. I will record the lecture and post it onto Canvas, so do make sure that you watch it. Any questions, please post them onto the discussion forum. That's it. Any final questions before we end? Okay, thanks, guys.